Good afternoon, everyone. So I would like to continue with the physical layer work. In this presentation, I would like to speak about waveform generation and framing. The outline is shown here. First, I would like to illustrate the work area of S32-3. Then I will dive a little bit into the waveform parameters, to be followed by talking about layer division multiplexing, bootstrap, and finally conclude with a brief review of the ongoing work on framing. So let's go first to the work area. I would like to use this block diagram of the physical layer that has been shown this morning by Luke, and to highlight the work area of S32-3. I used the smeared blocks in blue. Taking a closer look, these are the blocks with a description of the functionality and the purpose of each individual block. So perhaps I will not go into it. The goal of our group is to recommend the state-of-the-art technologies to fulfill these functionalities. In doing so, we wanted to consider these key attributes of the system: flexibility to support different types of networks, different types of services, robustness, reducing overhead to increase payload, power saving for mobile reception, reduced complexity so that we can have fast deployment, and so on, not to forget the extensibility to support current and future needs. So let's go first to the waveform parameters. The baseline supports 3 bandwidths, 6, 7, and 8 megahertz. It also supports 3 FFT size, 8K, 16K, and 32K, which trade off mobility and higher payload. The lower FFT size, which have larger carrier spacing, is well suited for mobile where we have high Doppler. And the high FFT size, such as 32K, is best suited for packing more data for static reception. In addition to that, we provision for adjustable number of carriers so that the broadcaster can choose how to maximize the capacity under various mass conditions, and also when the environment, RF environment changes, he be able to choose the bandwidth of the FDM signal. Continuing with the waveform generation, the next is the guard interval, which is a cyclic prefix to undo the effects of multipath. As Luke mentioned this morning, we have up to 12 different guard interval values that range from 28 to 700 microseconds. These will support different types of networks, ranging from MFN to very large SFN size. Of course, not all guard intervals are supported for every FFT mode. In choosing these guard intervals, we looked for a balanced and optimized values for all the supported bandwidths. And also, we considered how to best provide the overhead and channel estimation extent for each of the modes that you see there. The next aspect of the waveform generation are pilots. In this picture, you see a grid that represents 2 types of pilots: scattered pilots, which are shown in red, and continuous pilots. The scattered pilots are used for channel estimation, and the grid is parameterized by dx, which is the separation of pilot location in frequency, as well as dy, which is the separation in OFDM symbol in indices. We have larger flexibility with respect to echo range. You can see we have sorry, let me go back. On the upper table, you can see we have different range of pilots, different values of dx. And these trade off the overheads that these pilots take from the capacity of the M signal and the echo range that can combat to undo the effect of echoes. We have, in fact, two basic sets, one basic set that uses the extent of the guard interval up to 90%, but we have also another supplementary set that can be used to equalize for echoes that fall beyond the guard interval. The DY, we have chosen two values, one value that is optimized for high mobility, and we have a requirement to support 200 kilometers an hour for 700 megahertz, and we have a less dense pilot's DY024, which is optimized for fixed services. So if you'd like to spend some time, you can see how these pilots are recommended for different types of FT modes being used. The continual pilots are used for synchronization, and we have intelligently chosen CP indices that are randomly and evenly distributed so that we can do the best of tracking carrier frequency and offsets. And the overhead is very, very little. It's about 0.7% of the bandwidth. You can see on the top the CP indices are mirrored for 32K, and then they are nested to get the indices for 16 and 8K. This is a way how to reduce the memory requirement with regards to continual pilots. The last piece of the waveform generation that I would like to get into is peak to average power reduction. The baseline supports two complementary and optional techniques to combat high peaks of the OFDM signal. The first technology is tone reservation, where we spend about 1% of the carriers to carry reserved tone that will be used in time domain to remove high peaks. And the second technique is active constellation extension, ACE, which essentially take on the outermost constellation point and extend them into predefined sectors, as you can see in the picture. And these two techniques are complementary, like I said. The tone reservation is performs very well for high constellation densities like 1K, and active constellation extension performs extremely well in low constellation densities. Now let's move on to another block, which is the layer division multiplexing. This is a new transmission technology that has been recommended for the baseline. Like Luke and Lachlan stated, this technology superimposes two data streams on top of one another with different power levels, and this means different channel coding and modulation types. You will have an upper layer which is very robust and suited for indoor and portable devices. You also can have a second layer which can carry high data rates, and it can be used, for example, for 4K data reception. The power allocation between these two layers are essentially parameterized by injection level, and this injection level can vary between 3 and 10 dBs with the steps of a half dB. For example, if you use 5 dB injection, then you will allocate 24% power to the lower layer and 76% to the upper layer. In the table on the right-hand side, you can see reported performance for LDM using injection level of 4 dB. Next, I would like to quickly go over a bootstrap. In this figure, you will see a frame, an ATSC 3.0 frame. It starts with a bootstrap. And the role of the bootstrap is to have a quick and robust access to ATSC 3 signal by having fast initial synchronization and channel estimation. But in addition to that, it carries signaling such as versioning, ES wake up, and core L1 signaling. Looking under the hood, the bootstrap is composed of 4 symbols for the time being and can be extended if needed, B. And it uses 2 versions of structures that are shown in red, green. The first structure is CAB, and the other structure is, let me try to see if I can light up. Anyway, it mixes two robust structure, and this structure in time domain is very resilient to interference and very robust to detect. It also allows the receiver to estimate fractional frequency offset. The main part, which is in green A, is an inverse FFT of structure that is composed in frequency domain, as we can see in the next slide. Essentially, we have a zeta of Chu sequence modulated by PN sequence and mapped into 2K subcarriers, as shown in the 2 figures. And this is used for sync detection and service discovery by correlating the received signal with a predefined sequences. And then after that, we can use the knowledge of the PN sequence to have an initial channel estimation. The four bootstrap signal can carry 22 signaling bits using cycling shift of the zeta Chu roots. And they can carry ES wake up signal or wake up flag. It can carry also other core system parameters such as the bandwidth and baseband sampling rate. It also points to preamble structure. Next, I would like to quickly get into the framing structure. The group has recently reached an agreement on the overall structure of the framing. It is shown in this diagram. It starts with 4 bootstrap symbols in yellow. And these bootstrap carry, among others, configuration for the preamble, which are shown in blue, the 2 shades of blue. The number of preamble symbols are varied, and they carry signal configuration for the data symbols. And this signaling configuration can be composed of 2 types, static, layer 1 static, or physical layer static, and physical layer dynamic. Then we get into the data symbols, which are shown here in red, that carry the payload. We are working diligently to put meat on the bones for this structure. And in doing so, we are trying to keep an eye on these attributes, again, or key performance indicator. Essentially, we would like to have a flexibility to support variety service rates, multiplexing, resource allocation, and whatnot. We would like also to have this framing extensible to enable new needs in the future if the environment changes. We would like to keep an eye on layer independence, different layer, and enable power saving for a mobile device. So in summary, the baseline waveform parameters offer broadcasters a rich tool set that enables you to build up your networks with a large set of guard interval We have a different FFT size to enable different types of mobility from static to nomadic services. It also have a rich and efficient set of pilots to deal with different reception reception conditions. In addition to that, we have a bootstrap that provide a robust and quick entry to the ATS signal. It has a quick synchronization and allows you to send a fast and reliable EAS wake-up. It delivers also core signaling to the system so that it's easier to build a new system in the future with different versioning. The framing structure is being worked on right now, but it will provision for flexibility to support different resource allocation, power savings, and extensibility. I hope I didn't go too quick with my presentation, but if you have any question, please feel free to ask. Yes, Art.
You said 22 bits?
22 signaling bits, yes.
Defined, not existing.
Defined.
There are actually 24 bits.
True. So we have
22 are defined.
yes, true. Thanks for pointing that out. Just to mention that these can be also extended. Yeah.
Great.
Thank you
Very much.